Lieutenant Colonel Thompson here. I'm going to talk you through thermal control subsystem for Astro 310. And you got to bear with me. I don't have exactly have a professional recording studio here, but got this white board on the wall in the corner of my basement room, and I'm going to talk you through. It might be hard to read some of these equations and some of these words, but again, everything in here is in your book and on your equation sheet as well. So again, starting out with a thermal control subsystem. This is why do we need a thermal control subsystem? Well, basically, we want to keep our spacecraft in a temperature comfort zone, so to speak. You know, you can launch a spacecraft. Some spacecraft, we don't really care about the temperature inside, but most active modern spacecraft, we have to keep the temperature in a certain zone for the payload and the other systems to operate correctly. So we're just trying to keep the satellite in that correct temperature zone that we want to reach. And how are we going to do that? Well, it's a balance between the heat in and the heat out. That's what it is. We got to keep, there's going to be sources of heat coming in, and there's going to be some heat going out of our spacecraft. We've got to keep those balanced in equilibrium to keep the temperature in that comfort zone that we want to stay in. Okay, so how does heat flow, or how does heat transfer occur? And there's three main mechanisms, the first being conduction. This is just a physical contact between two objects, or a single object where the heat can flow along the object. Like in your book, it talks about a metal rod being heated on one end, and you can feel the heat on the other end eventually as that heat is conducted through that rod. Or two objects coming together, when they physically connect like that, the heat can transfer from one object to the other just by them being physically connected. The second type of heat flow or heat transfer mechanism is convection, and this requires a fluid flowing in contact with the object, the source of the heat. And that fluid needs to be flowing so it can be forced by something like a pump, like in your car cooling system, your engine cooling system, or it can be done by the gradient of gravity with the changes in density. The gravity can just naturally set up that circulating fluid to remove heat from the system by convection. And the third system that we talk about is radiation. And this is just electromagnetic radiation. Every object of mass which has a temperature greater than absolute zero is going to radiate electromagnetic radiation to some extent. So those are the three types of heat transfer, the three major types. And in space, we really only have radiation. That's really our only option for removing heat in and out of a spacecraft, is to radiate it, because there's no physical contact with other objects. There's no air. There's nothing. There's no fluid that's circulating around the spacecraft. So we really have to work with radiation. Okay, so we have four major heat sources that we have to deal with in the space environment, and three of them are natural. And you can see here the sun generates heat at about 1358 watts per square meter. And albedo, which is the reflected sunlight, the sunlight that's reflected off of the Earth and strikes the spacecraft, and that rate is about 407 watts per square meter. And then there's the Earth radiation. The Earth is a warm object, so it's also radiating as well. And sometimes we call that Earth shine because it's radiating from the Earth. And that's about 237 watts per square meter. And those numbers are on your equation sheet as well as in your book too. So you don't have to memorize those. Those are on the actual equation sheet. And then, of course, there's the internal heat generated by the mechanisms inside the spacecraft, the motors or the computers. All those mechanisms and systems generate heat that's just inside your spacecraft. So you have to factor that into the equation when you're talking about the balance between heat in and heat out. So we have all these sources of heat coming into our spacecraft. Not all of that heat energy is actually absorbed into our spacecraft. Some of it could be reflected, some of it could be absorbed, or some of it is just transmitted. In other words, just passed right on through and re-radiated by the object. So we have some coefficients that we use to quantify those different properties. And the first being reflectivity, which is a Greek letter rho. And that's just the amount of energy that's actually reflected from the object. And rho is going to be a number between 0 and 1. All right, the amount of heat energy that's absorbed is characterized by the absorptivity, or alpha, which is also between 0 and 1. And then we also have the transmissivity, which tells us how much of that heat is transmitted or passed through the object. And its Greek letter here is a tau, which is also between 0 and 1. And it turns out that we have to reach a balance between these three different characteristics here. So tau plus alpha plus rho is going to equal to 1. And that's on your equation sheet. All right, so we have these different sources of heat, and they're going to interact with our objects in a different way, depending on the properties of the objects. But we can actually quantify the total heat in, or Q in, as the amount of heat arriving at the spacecraft, or the heat that's coming in, times the surface area of the spacecraft, times the absorptivity of the spacecraft, the surface of the spacecraft. So we have the total heat that's available coming in, times the surface area, times the absorptivity. That's going to tell us the amount of heat that's actually coming into our spacecraft. All right, so that's how we model Q in, or the heat in. The heat energy going out, or Q out. To model that, we're going to use the Stefan-Boltzmann equation. And this is just going to be the Q out is going to equal sigma, which is the Stefan-Boltzmann constant, 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. And again, that's on your equation sheet. You don't have to memorize that constant there. So heat out is equal to that constant, the Stefan-Boltzmann constant, times the total emissivity. And emissivity is just a factor between 0 and 1. Just similar to these heat in properties, the emissivity tells us how much of that heat is leaving, or how easily it is leaving a certain object. So it's just a factor between 0 and 1. And then there again is our total surface area. And here's our temperature to the fourth power, and that's in Kelvin. So temperature in Kelvin. So, and again, on your equation sheet, there's a connection between temperature Kelvin and temperature Celsius. So that's on your equation sheet as well. You don't have to memorize that. Just be careful. If you're working in Celsius, you need to convert to Kelvin before you actually use these equations here. All right, so we have our heat out, our heat in, our heat out. And again, the whole point is we're going to balance those two. We're going to balance heat in and heat out. And that's going to, once we're in equilibrium, we're going to be operating at a certain temperature. So we can actually solve this equation for the temperature, the equilibrium temperature. And you can just move all this over to the left side, take the fourth root. But this is also done on your equation sheet, so you don't have to do it yourselves. So we solve for the equilibrium temperature of the cube in this case. This is going to be the fourth root of the Q out divided by sigma, emissivity, and alpha. And again, we take the fourth root of that to get the temperature here in Kelvin. And my calculator, there is no button for the fourth root. You won't find a button like that, I don't think, on any calculators. So the way you take the fourth root is to just raise it to the 1/4 power. That's the same as taking the fourth root of a number. So you plug in your numbers here and then raise it to the 1/4 power to solve for your equilibrium temperature. Okay, that's all I had for you today. There's examples in your book. There's a really good example on, it's on page 594 in the book. So if you want to work through that and watch the rest of this video, and then I'll be online as well to answer questions along with the other instructors. All right, have a good day. Thanks.
Hey everybody, it's Major Cunningham coming to you today in coronavirus lockdown from my study where I just do all my typical videos. Good to hopefully see you guys. I know you're here in spirit with me. I know you're here in spirit with you. And I am there with you. So, anyway, while we are living vicariously over the internet, let's do some math and talk about thermal control. So, Colonel Thompson gave you a great overview of why we have to do thermal control with a satellite, right? There's no air. I have to find another way to get heat out. And I've always been surprised, kind of, you never suspect the satellite will be generating that much heat internally, right? But just like your computer at home, will get hot when you're running a particular application that uses a lot of computing power. Same with satellites, and their computers aren't usually even as fast as yours. So anyway, they're dumping heat, and it has to go somewhere. And so this math kind of shows the math. I was going to say this math shows the calculus. It's not actually calculus. This math shows the thought process that goes into that. So without further ado, let's get into last year's homework problem as we do, and we'll press. Okay, FalconSat X. So actually, this is a real thing. FalconSat X or FalconSat 10 is our current FalconSat that's in the design stage, and we already have FalconSat 8 is mostly built, and FalconSat 6 is on orbit, and we always have another FalconSat kind of in the oven, if you will, and FalconSat 10 is the one in the oven. But anyway, it's another, if you guys have seen, when I've showed in FalconSat, it's basically like a little mini fridge sized satellite that is roughly cubic, looks a lot like a cube. And so when we give you these what kind of seem like horsey-ducky fake assumptions, they're actually pretty true for FalconSat. FalconSat is pretty close to a cube. It's got some antennas and it's got some little things on it usually, but most of it looks like a box. So anyway, FalconSat 10 has selected a combination of thermal coatings, let's assume, for each of its 6 3-square-meter sides. So let's see, I'll do my best rendition of a cube. Oh, that's actually not as bad as I usually draw. Ask all my classes, it's not good. The art part is not good for me. Got the sun over here. Oh, I probably could have drawn the, tell you what, this would be the Earth. There's a continent, and there's a continent, and there you are, and you're happy. There's the sun. Okay, so just kind of as an overview, the sun is pumping out, right, lots of radiation. That's what the radiation sounds like if you could hear it. Just kidding. Okay, this is to the tune of 1,358 watts per meter squared. That's a lot, right? Same as you would feel standing on the Earth during a summer day, right? That's hitting you with a little bit less, but nearly 1,358 watts per meter squared. You can impress people with that fact at the cocktail party. Duh. All right. The sun is also putting out radiation that hits the Earth and then bounce back up to the satellite. Call this albedo. And the reflected amount is 407 watts per meter squared. And the Earth itself radiates one side. We call this Earth shine, right? The Earth itself, you wouldn't think the Earth is hot, but compared to the absolutely frigid background of space, it is warm. So the Earth is even contributing a little what we call Earth shine to the tune of about 237 watts per meter squared. So you can see this satellite's taking heat from 3 different sources, and not only that, I'll draw a little, zoom in. All the different wheels and circuits, and I don't even know how to draw it. All the stuff inside the satellite is producing heat as well. And we're going to call that Q int for Q internal. Let's see. So they give that to us. So FalconSat X requires 450 watts of power continuously. So Q int is 450 watts. It's going to come in handy in just a little bit. So, well, that said, what we need to do first is we need to calculate what our Q in is, how much heat is actually coming into FalconSat based on how big it is and if it's in the sun or not. We're going to calculate our Q out, which is the amount of total heat the satellite has to manage. Basically, all that does is accounts for all the heat coming from the sun and the Earth, and then adds in the internal electronics and the heat that they're generating. That will give us the temperature. So each of these is their own equation I'll walk you through. But this gives us the temperature that we're going to need, or the temperature that the satellite will settle at, basically when it's in the sun, and it's vented as much heat as it can, and it kind of reaches a state where the amount out equals the amount in. We call that the equilibrium temperature, right? Equilibrium temperature. So let's walk through that process now. on your equation sheet. It's under environmental control. We're actually, well, my vote hopefully is to change this to thermal control subsystem, as far as the bold text goes. Environmental control really refers to manned spacecraft. That's not the Air Force's thing, if you will. It's not the Space Force's thing at the moment. Could be in the future. Our astronauts work for NASA. That's manned space flight. Like you'll have Air Force folks that go over and become astronauts, and Navy folks, and DoD employees, basically DoD military folks that become astronauts. But it's not like Space Force is launching spaceships like the Enterprise or something. So anyway, environmental control applies to like the shuttle, the Soyuz, the ISS. Thermal control is what we generally call it when we're just trying to manage heat on a satellite, an unmanned craft. Okay, let's begin. Okay, let's see. I'm just going to write the Q in equation. The total amount of heat going into this satellite equals the heat input, which I'm going to show you in a second, times the area of the side of the spacecraft that's taking all this heat. We're going to assume it's just coming into the spacecraft on one side here. Or you could also say, well, the Earth shine's coming from below, the sunshine is coming from one side, and the albedo's hitting another side. Doesn't matter. You're just going to assume basically that all the heat sources are hitting one side of the satellite. So the area of one side, and then multiplied by this thing called absorptivity, which is like basically how much of it does FalconSat suck up and hold on to, and how much versus how much gets bounced back out or retransmitted. So, okay. Heat input. Let's begin with that. So what kind of heat is coming into the satellite? Well, we have 1,358 watts per meter squared from the sun. We have 407 watts per meter squared from albedo. We have 237 watts per meter squared, double checking those numbers, from Earthshine. The area of one side is 3 square meters. And the absorptivity, they tell us, let's see here. Yep, is 30%. Well, guess what? You need that in a decimal, so convert that to a decimal. Okay, and then we are hungry, so we crunch some numbers. We plug and then we chug. Coronavirus cannot stop us from plugging and also chugging. Satellites can't get viruses, not coronaviruses. So I get this to be 1801.8 watts. Can I get a watt? All right, cool. All right, so check. Now let's find our Q out. So this is basically just taking all the heat that's coming into the satellite, which we just calculated, and we're going to add Q internal, which they told us the FalconSat is using, which is to say putting out 450 watts of power. So 1801.8 plus 450 equals, what does it equal? 2251.8 watts. So the amount of heat that FalconSat needs to get rid of to manage, if you will, is 2,251.8 watts. Okay. So what that means is we're going to use this T cube equation, which is kind of written specifically for objects that are a perfect cube. And we're assuming FalconSat's a perfect cube. And like I said, that's a pretty good assumption. So it's the fourth root of the Q out we just found, right? The amount of heat we need to manage, over the Stefan Boltzmann constant, the area, again, that area of one side, and the total emissivity of the spacecraft. Okay, so Q out we found 2251.8. Good. Stefan Boltzmann is on your equation sheet where? Let's see. It is right in the environmental control area, because that's pretty much the only place we use it. Again, I want to call it thermal control, but it's the same thing. 5.67 times 10 to the negative 8. And then, of course, 3 meters squared on one side. And the total emissivity, they tell us, total emissivity in the sun, which we're assuming it's in the sun right now. What is the equilibrium temperature in the sun? So the total emissivity in the sun is 2. We'll raise that to 1/4 power, which is the same thing as taking a fourth root of something. calculators, I don't have a 4th root button on my calculator. I don't know about you, but I can always raise things to the 1/4. Right, let's plug chug. That gives us a ridiculously huge number. Raise that to the 4th to get that back in sane terms. That gives me 285.23 Kelvin. Now, the problem doesn't say in Celsius, but people won't live their lives in Kelvin. They live their lives in Fahrenheit and Celsius. So for funsies, because it is so fun, let's convert this to Celsius. Up here, we do this equation for you on your equation sheet. So if you need to go from Kelvin to Celsius or Celsius to Kelvin, you can use this equation. So I want to get the Celsius version. So I'll subtract the Kelvin's value I just got from the conversion factor of 273.5. This gives us 12.08, I guess, degrees Celsius. So anyway, this was correct. You could stop there. This just makes a little more sense. So anyway, that temperature, even in the sun, because FalconSat is emissive enough, it actually stabilizes at a pretty same temperature. Like you could survive at 12 degrees Celsius. You might not be comfortable, but you probably wouldn't die. So anyway. Great, so that's kind of starting off with Q in, Q out, going to temperature. Another way you might see this is this problem right here, which does a couple of different things. You know what, I can still see my paper under that. Go ahead and rip that up, put that inside. Okay. Let me get organized here. Stuff out of the way. Okay. All right. Number 2 says, in order to protect the electronics, FalconSat X designers, FalconSat 10, would like to minimize temperature swings in the satellite. How nice. Calculate the total emissivity required. So we want to know epsilon total required to maintain an equilibrium temperature of 20 degrees Celsius in eclipse. So, okay, first of all, it's different from the previous problem because it wants emissivity and not the temperature. It gives you the equilibrium temperature right here. But the process, other than that, looks pretty much the same. The other difference is we're in eclipse, not the sun. So what is eclipse? Well, you have the sun. I know this is intuitive for most folks. And the Earth, right? And the satellite happens to be at a point in its orbit that is behind the Earth. So it's shielded from the sunshine. It's shielded from albedo because, well, what is there to reflect off of, right? All the reflected radiation, albedo goes off in different directions. It can't go through the Earth to get to the satellite. So really all that is hitting the satellite is Earthshine when it's behind the Earth. So that's our heat input. Our heat input is just what the Earth is radiating, which, like we said, it's not insignificant, but it's not much compared to the sun. So let's begin. So our process looks the same. We're going to find how much heat overall is coming into the satellite, how much heat needs to go out from the satellite, because remember, Q out takes into account all the heat generated by the onboard electronics and machinery and reaction wheels and all that. And instead of finding temperature like before, we're going to find emissivity total. That's what we want. So really the process looks almost exactly the same. So okay, Q in. Same equation as before. Heat input. Oop, times area times absorptivity. Okay. Our heat input is different, right? Because we don't have the sun, we don't have albedo, we only have Earthshine, so that's only 237 watts per meter squared. The area of one side is still the same. We're assuming that only one side is, taking all the Earthshine. And that's not a valid assumption in the real world, but for core Astro, definitely a valid assumption, and you should assume that. Absorptivity from before, because this problem is like talking about the same scenario, 0.3. Let's let's see here, 237 times 3. Boom, boom, boom. I get that to be 213.3 watts. Now we'll do our Q out as before. Q in is just a little bit lower. But the onboard electronics are still pumping out heat from the battery, right? They're still running off a battery. So Q in that we just found, 213.3 plus 450, that gives us 663.3 watts. Now, this is a little different. Remember how last time we used this T cube equation to find the temperature of our cube? Well, we're still a temperature of a cube, but we're looking for, we can rearrange either this equation or this equation. These two are kind of brothers. They're just rearranged for you, so you don't have to go through the mental gymnastics on a GR. But they're two sides of the same coin. These are the exact same equation that's rearranged. So it's easier for me to just take the Q out equation and then isolate emissivity total from that. Okay, T of 4. Okay, so emissivity total, the Q out that we just found over Stefan Boltzmann area, temperature to the fourth. Now, this equation, these equations, use Kelvin. Okay, why? Because Stefan Boltzmann's constant is in Kelvin to the fourth. So don't plug in degrees Celsius. Let's really quickly just convert our temperature. I don't want to write T. Well, actually, how about this? Temperature in degrees Celsius equals 273.15. Gosh darn it. I want kelvins, not Celsius. Apologies. Okay, so temperature in kelvins equals 273.15 plus whatever the temperature was in degrees Celsius. So that equals 273.15 plus 20 degrees Celsius is what we were given in the problem. So that comes out to 293.15 Kelvin. That's what we're going to plug in here. So here we go. Q out, we discovered in Eclipse was much lower, obviously, because we're not taking as much heat in. Good. So over that, and then 5.67 times 10 to the -8. If you're interested in the units, watts per meter squared, Kelvin to the fourth. That's what the units are for that. The area, still 3 meters squared, right? That's the area of one side that's taking all the heat. And then T to the fourth, not 20 degrees Celsius, 20 degrees Celsius in Kelvin. So 293.15 raised to the 4th power. Should give us something not crazy, hopefully. Good. So I get the total emissivity to be 0.53. You know what? I'm kind of a 3 digits sort of a dude. It's just how I live my life. 527. Ta-da! What are the units on emissivity? Unitless. It's a ratio. Okay. So, all right, just to recap, what we found in the first problem was the equilibrium temperature based on us being in the sun. Problem number 2, we were looking for the, we could have been given the emissivity and looking for the equilibrium temperature. You guys know how to do that, but in this case we were given the reverse, which was, here's the temperature we want to achieve. How emissive do we have to be to achieve that temperature? And then they said, not only that, I'm changing the situation on you. You've gone back behind the Earth, so now you're in eclipse. So as you can see, the processes are actually really similar. That's why there's only a couple of equations right here for TCS, for thermal control. All right, problem 3 is a conceptual one. I'm going to let you guys hunt for that in the book. It should be very easy to find, P.S. So thanks, and we'll talk to you guys next time. Stay cool.